Let's examine the chain rule for differentiation. We use chain rule when we're trying to find the derivative of a complicated function that bears some similarity to one of the common functions whose derivative we know. A few common functions and their derivatives are listed below. And I have an example that we can do chain rule on. It's 2x to the third. Find the derivative of that. So the first thing to look for is, does our function bear similarity to one of the common functions? And if you look in the table, you'll see that it's most similar here to an x to a power. For example, if the problem had simply been x to the third, find the derivative of that, it could have been a fairly easy problem. We would have used power rule for it. It would have become 3x squared, and then we would have been done with the problem. Now ours is similar to that, and we're actually going to use that x to the third in our chain rule analysis. So we want to let f stand for the function that our function is similar to, x to the third in this case. It is called the outer function because we actually have a composition of functions. It's one function inside another, and the outer function is something to a power of 3. And that brings up the question of, what is g? So g here is the expression that's complicating things. It's the expression where if you were to take it out and replace it with a g, then that would simplify the function into just one of the commonly known forms. So if g were to take the place of 2x here, then we would have g to the third, which is just a simple power rule type of situation. Okay, so let's let g equal 2x. And so you might be thinking at this point that maybe we should make our final answer here 3g squared. Like, is that the right thing to do here? It turns out not to be the right thing. And in order to prove that it wouldn't work here, I'll actually find the derivative of 2x to the third using other means. 2x to the third could be rewritten as 2 to the third x to the third. And if you want the derivative of that, you could find the derivative of 8x to the third, which would be 24x squared. So that is actually the final answer that we're looking for here through chain rule. And let's see whether it would work or not to replace our expression with 3g squared. We would have to now go back and plug in the 2x for g. But if you do that, you'll see this is going to come out 12x squared. So for some reason, this approach does not work. And why not, you know? Well, we have to be more precise about what we mean when we say take a derivative. So the prime notation is really great for just indicating that you want a derivative taken, but it doesn't make it clear what variable we're taking the derivative with respect to. So we could use another notation, the Leibniz notation for taking a derivative. And what's great about that one is it makes it clear here that we're taking the derivative with respect to x. And I think we can all agree that that's what's implied by the problem when it says take the derivative of 2x to the third. And so that's the issue here, is that we're not taking the derivative with respect to g, are we? It's a derivative with respect to x. That's why it's not just simply 3g squared. See, if it had been d over dg of g to the third, well then, no question, it would have been 3g squared, and that would have been the end of it. But this is d over dx of g to the third. So there's a mismatch with the variable in our function versus the differential in the denominator here. And that is where chain rule is going to come into play. So on the next page here, I will show how to use chain rule in this situation to find the correct derivative. So in its most simplest, concise written form, if you're trying to take the derivative of a composition of functions here, then we need to find the derivative of the outer function, leave the inner alone, and then multiply by the derivative of the inner function. That's what chain rule says. But why? Why does that work? So let's go back to our assignment of f and g here in our problem. F of x was defined as x cubed, and g was defined as 2x. So if we want to find f of g then, and let's just start with that, well, that would be as simple as just g to the third. Now let's take a derivative of it. But instead of just writing it with the prime notation, let's write it with the other notation. That's what we want to find. So why didn't it work when I had written this? Like, why is that not valid to do? Well, it should be clear here that if I write it a little more concisely, that my denominators here clearly don't match. So it's not valid to take the derivative with respect to x on one side and the derivative with respect to g on another. That's why the approach didn't work. But could we make a modification to this to make it work? What would it take? Let's multiply by another term here. And it should be clear now that if we were to multiply by dg over dx, the sides really would be equivalent now. That's chain rule. It's another way of writing it. So let's try to go back to our problem and fix the problem. It doesn't work like this, but it would work if I were to do this. Now it's valid. So I'm going to need to know what dg over dx is to complete this. So I'll go back to my original assignment of g, and let's just go ahead and find dg over dx. It will actually be 2. And we're just going to want to take that and plug it in here. So we'll get df over dx equals 3g squared times 2. We have to multiply by the derivative of g. That's part of chain rule. So what will that become? 6g squared. And let's go ahead now and replace our g with a 2x. And then we finally arrive at the answer that we were looking for, 24x squared. As you can see, it matches with what we said the true derivative was, 24x squared. That's chain rule.